So up next we have Dan Bowman. He's going to be talking about exposing the technical and commercial factors underlying internet quality of experience. So I'll let you take it away. And we're running just like 30 seconds ahead of schedule too. So.
All right. So I was glad to see that a lot of the earlier speakers talked about latency and particularly timing between SYN and SYNAC, because that's one of the core things I'm going to be talking about here. So what we did, so my name is Don Bowman. I'm from Sandvine. And what this is a perspective on a consumer access network. And what we did this study last summer, and we took a set of participants in the United States, 5 MSOs and 1 LEC. And what we did is we looked into quality of experience, and we looked into it from a particular angle of, what quality did the user achieve, and if it wasn't perfect, where might the impairments have been introduced, and what motivations might there have been for those impairments, whether they were technical or commercial, etc. And the second is we wanted to sort of demonstrate that quality was an end-to-end concept. In some cases, there's decisions that can be made by one player that can be corrected by another player along the route. So somebody could choose a more expensive path, and the next guy could just pay more. And there's some decisions that are uncorrectable. Like, for example, if you're streaming video and you decide not to put high-definition video out there, there's no one along the way that can fix that. And then along the way, one of the things we discovered is a lot of the existing sort of consumer-branded benchmarks really didn't do a very good job. They weren't actually all that repeatable. They were giving a lot of noise. So we looked at a bunch of different factors, but the primary two I was going to talk about today was one about the concept of streaming video as a proxy for quality. So there's 2 primary types of streaming video on the consumer internet today. There's what's called adaptive video, and what adaptive video does is you sit down to watch a really long movie, and it chops it up into little chunks, and each chunk as it comes to you, if it comes too quickly, your client asks for the next chunk at a higher bit rate, and if it comes too slowly, the next chunk it asks for a lower bit rate, thus avoiding stalling at the trade-off of some fidelity. And the second type is progressive downloads, where there's a really big file on a server that kind of bursts it towards you and then waits a little bit and bursts it towards you, and that's where you get the stalling. So one of the things we looked at was the consistency of the delivery of video streams, and then we kind of tried to break it down by CDN, by BGP AS path, by content type, by device type, etc. And one of the things we found is this was actually very difficult because, of course, there's multiple paths involved. A single video provider may have 2 peers, and those 2 peers would connect to the access network, and one flow would go one way and one another. And then that video provider might in turn use 3 CDNs, each of which would have 2 peers. So as a consequence, you got a lot of sort of distributions that had multiple different distributions mixed together. It was very, very difficult to get the sort of the signal from the noise. So the other measurement that I'm going to talk about in here a lot is about round trip time. And what we did for that one is we used the delay between TCP SYN and SYNAC at our location point as a proxy for the internet side of things. And we used the delay between SYNAC and ACK as a proxy for the delay on the access side. And then what we did is we looked at variations in those. So rather than looking at the absolute value of the latency, we looked at whether it trended up and down during times of congestion, because what we were assuming was that the majority reason for a delta in latency at different times would be congestion or queuing in the routers. And one of the things we did in that part of the benchmark is we looked at just the top 100 websites. We didn't really want the long upper tail of somebody's home server serving stuff. We just looked at the best peered things. So when we look at the top popular quality benchmarks, there's sort of 3 that we looked at that are sort of, I say consumer branded, but these are things that the mass market understands. These are things that are printed in USA Today and so on. And the first is Ookla's Speedtest.net. So Speedtest.net, very simple user GUI, whether it's on an app on a phone or it's a web page on your browser. It gives the user kind of a speedometer level upstream, downstream, and sort of latency ping time view. And the second one we looked at was the Netflix ISP Speed Index, which talks about the delivered speed of Netflix flows to users in a consumer access network. And the third one we looked at was YouTube. Now, subsequent to this paper, YouTube has come out with a new methodology, which is actually quite nice. And the Netflix one has made some changes to their benchmark, but you'll get the idea from here. So the first thing we did is we looked at the quality of Speedtest, and we said, well, let's run it multiple times, and we'll see how consistent the results are. So if you can try this experiment at home, you go home, you run Speedtest, it suggests a couple of servers to you, and you'll find that the results are dramatically different. And one of the reasons they were different is they often took different routes. Like one would be directly peered and one would go through transit. Another reason we found for differences was the servers were often set up dramatically differently in their TCP windowing. And as a consequence, what we found in practice, every country we tried it in, there would be something like a 10-to-1 variation from the best Speedtest server to the worst Speedtest server at the same instant in time at the same access location. So unfortunately, although a lot of people say that's the killer application for LTE. First thing everybody does, they get an LTE phone, they're on speedtest.net. Right? It's the first thing I did. And it sort of sticks in your mind forever. And I got a lucky run. I got 50 down and 25 up. I was pretty happy. And somebody else might have got a crummy run. But it effectively wasn't very consistent. And we see some different results here. So here's, for example, one of the staff in our company ran this at home, and he's on Comcast's 105 megabit service. So under ideal circumstances with no latency or no jitter and no congestion and yada, 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 he'll get 105 megabits. And what he found is that the best server for him was about 90 megabits down, and the worst server was about 22 megabits down. And you'll note that the latency on those is relatively similar. If you do trace routes to those servers, what we found is that they were relatively similar distance by a hop count away, relatively similar distance by latency away, and presumably not very congested. But they both made very, very different opinions on how TCP was set up. The operating system was different on the two servers. And then the same for AT&T's UVerse on the bottom. The worst server was 3 megabits. The best server was 17 megabits. You note that there's two servers that are relatively similar bandwidth that they're showing, about 17 megabits, with one has 2x the latency of the other. So the takeaway from this was, speedtest.net was not an effective means of diagnosing end-to-end bandwidth from a consumer standpoint, because it was effectively giving a different number every time you ran it. And there's lots of different things that we suggested to improve to sort of make it better and better and better. But it was every country we tried it in. The most interesting one for me was Singapore. The entire country is 20 kilometers apart. There's really only 2 network providers there. And you would run Speedtest server 1 and you get 100 megabits every time, and you run Speedtest server 2 and you get 20 megabits every time. And it was really just random. So that's what this one shows here, is the different results that we got on that. Again, 90 megabits down, 70 megabits down. The next one we looked at was the streaming video. And as I mentioned earlier, the streaming video is adaptive. So as a consumer, you sort of don't see this behind the scenes. There's several different video providers that are adaptive today. So what we did is we benchmarked Hulu and Netflix against each other. They use very, very similar sets of technologies, but they're hosted by different companies in different fashions. And one of the things we found over the course of the study is that they behave differently. So the Hulu one would deliver relatively consistent quality, where we would see a dip in quality on some of the operators at certain times. But the other thing we found was a lot of people, as we talked to them, they didn't really understand what this speed index was showing. So what this speed index shows is the demand by a consumer. It isn't really a measure of end-to-end bandwidth. And the demand is based on a set of different factors. One of them is your device type. Netflix at this time would only deliver Super HD if the OpenConnect server was directly inside the network, not if it was on a peered network. They would deliver Super HD to a Windows 8 device, but not a Windows 7 device. And as a consequence, you ended up with big variations due to device mix and due to how peering was set up. And you could sort of work around it. You could change your DNS server and then get the other Super HD server, et cetera. But what we found is that the numbers that were reported here, they did come out in our survey, and they were pretty accurate with respect to what the users were achieving, but the reasons they were achieving it really didn't have anything to do with the access network. When we looked at it a little deeper, what we saw is a couple things. First of all, at this time, Netflix used 4 different CDNs to host their traffic. They used Akamai, Limelight, Level 3, and their OpenConnect. And all ISPs in the survey, all 6 of them, experienced a little peak in OpenConnect in the wee hours of the morning, some sort of an experiment that's running. And they all showed variation in volume per CDN and time of demand And they all observed some quality dips some of the time, but none observed dips all of the time. So what we do when we look at the bandwidth, so what this chart shows is the per stream bandwidth over 24 hours, over 7 days. So it's brought all into one chart. So all the peaks are lined up. And you see that at the time we did this, the Akamai one was delivering a consistently lower bit rate. And the reason for that is largely the device type. It was really preferred by your small screen devices like your phones and so on. And then we found the other CDNs didn't really have a trend line. But this is brought together from multiple different service providers. When we broke it out by service provider, we could see there was a strong preference for one CDN at one time of the day and a different CDN at a different time of the day. Perhaps there's a different billing model. One CDN might be paid, per peak rate. One might be paid per average rate. There's a decision made in the routing path here that's more than just randomness or equal cost multipath routing. But the neat thing we sort of found about this is there really wasn't a trend line. Over the course of 24 hours times 7 days, all 6 operators delivered more or less constant quality to their users, implying that there wasn't a sustained access congestion issue preventing it from going higher. And when we compared it against Hulu, we saw effectively the same thing. So the conclusion we sort of came to there is, congestion exists in some places some of the time in the access, but in this survey there was something like 8 million consumers. It didn't exist in all of the places all of the time. And what that implies is that the next spot for investment is probably not the access, but might be the backhaul or more likely the peering interconnects. One of the other things that we looked at, again, I'm focusing a little bit on Netflix here, but we looked at a bunch of different video providers, is we used the server latency as a proxy for where they're served from. So you could make the assumption that if I was hosting video and I didn't pay for transport across the United States, I'd probably serve the West Coast users from the East Coast and the East Coast users from the West Coast. It would offset the peaks in my servers. I'd use a lot less virtual machines that way. It'd be cheaper for me. And so when we looked into that theory, it didn't prove to be true. One thing that was interesting is that in this chart we're showing the OpenConnect East and West and the others East and West. The others East and West stayed roughly similar latency over the course of the day. And the OpenConnect, it rose at exactly the same instant in UTC on both sides of the continent simultaneously. But the latency is so high, it seems to be more of like a virtual machine management strategy or something like that. So one of the other things, we found that Netflix was the only video provider to have latency scale with load. And one of the other things we talked about in here is it's very difficult with TCP to do sort of rate control. TCP was really intended to go as fast as it could without causing undue congestion to the other flows. And as a consequence, when you have something that is sort of isochronous like video, there's a bunch of different strategies for how you pace it. But effectively what you're doing is you're clamping down on the transmit or receive window. And Netflix actually does a fantastic job of this on the OpenConnect. And that's one of the other reasons that the latency seemed to be higher compared to some of the others. So what we concluded from our study is that the Netflix ISP speed index was not an effective way of measuring the quality of an access network. We found that the access networks we were in would consistently deliver sort of 5 megabits of Hulu 24 hours a day, would consistently deliver about 3 megabits of Netflix. And really what the number was showing was based on the decision to not stream Super HD to people who had not brought the appliance into the network, was based on device mix, and was based on peering arrangements. It really wasn't related to the access side. But this is something that from a consumer standpoint, the consumers really focus on. They have exactly one business relationship, which is the access. So it was very poorly understood with the people that read this. One of the other ones we looked at was YouTube. So at this time, YouTube was very much burst-paced to the users. So YouTube was a big file that was downloaded to you in your browser, and they would sort of on, off. And YouTube had a set of charts that would sort of show the rate that was achieved there. And the YouTube charts were actually, they were quite accurate in terms of measuring the peak rate that was there. In this particular example, that we're showing, a screenshot that a user would have got in Time Warner's Dallas area. And from their house, they got about 8 megabits measured for their ISP, but 8 megabits for the area. And when you look on the capture we did in Wireshark, YouTube was achieving about 8 megabits. But is that really a true measure? So when we dig under it and you look on very short time horizons, it turned out that YouTube was effectively pulse width modulating. So what happened, it would go 25 megabits, then 0, then 25 megabits and 0, which is very inefficient from a network standpoint. It's very difficult to go very, very smooth, but unfortunately these sort of peak waves can line up. It's not a big deal when you're talking about sort of a 100 gigabit link shared by millions of users, but when you start getting out to the little tippy edge of a network and you're talking about a DSLAM served by 8 bonded T1 IMAs, that becomes a big deal when you and your neighbor's peaks line up. And this was actually something that was very easily observable. So one of the things that we sort of assessed with the YouTube benchmark, at that time, it was actually not a bad sort of proxy for the overall rate in the home. It was actually at least as accurate as speedtest.net. So in this particular case, my modem, this is from my house, my modem is rated to sustain about 40 megabits, and I was getting about 30-something megabits on YouTube, which was pretty good for me. One of the other interesting things we observed, and this was very specific to YouTube, YouTube was the only video provider of the dozen or so we looked at in the study that had two dips in quality or the rate of delivered stream. They had a dip around noon hour, and then they had a dip again sort of in the peak hours, sort of 6, 7, 8 p.m. And this was correlated across all 6 networks, so again, roughly 8 million consumers. So it's a pretty strong thing. At the time, I drew the conclusion that it was a first mile issue on the Google side, that it was either server capacity or links there. And subsequently, someone suggested, which was actually a good, very interesting suggestion, that it might be a device mix ratio. At lunchtime, people are out and about and they have their cell phone and they look at a clip of a cat playing a piano, and the cell phone draws a lower bit rate because it's got a smaller screen, and then it might actually be a smaller demand at that hour of the day. But it is something that it does seem to be impacted by congestion during the peak hours here, because it is delivering a markedly different bit rate at peak versus off-peak hour. There is some degradation in quality. So when we looked at it against the other providers that were on the same axis at the same time, so when you sort of compared YouTube to HBO Go, when we compared it to ESPN, we compared it to Hulu, they did not see this. So again, our conclusion was at the same instant in time, 8-ish million people using YouTube would see a dip, using HBO Go would not see a dip. The conclusion was that as an independent variable, we could rule out the axis and the backhaul for us. So what we did is we found that YouTube measured against the average delivered speed and reports the relevant comparators. So I think that was very good. The YouTube one is very, very transparent, and their new speed test thing is actually quite good as well. It's a little bit more skewed towards the easy for consumer to understand and less for people like me, but it's still quite good. It's a little bit flawed in that it doesn't actually measure connection speed, which is a very difficult thing to do. It doesn't purport to do that. It just says this is the YouTube speed you achieved, but a lot of people sort of misinterpreted my YouTube speed from my actual connection speed, and then they get into this sort of headspace about I'm paying for a 100 megabit connection, YouTube's only achieving 8 or 10 megabits, am I really getting what I paid for? And again, we think that there's some congestion being experienced here even when the network has excess capacity. And the last big measurement we did in this study, which is where the latency comes in. So what we did is the way our system works is it measures a lot of sort of very detailed things. And one of the things it measures is the top 100 domains, top 100 HTTP domains by hits and by bandwidth. And what we did is we used that as a proxy for the things that will probably be very well peered, very well connected, professionally run data centers, so that we could weed out everybody's home web server. And we created a sort of an index, a quality index based around the top 100 domains. And again, we looked at the latency of where we were to the server and back, and the latency of where we were to the client and back. And we used those to sort of gauge in aggregate the congestion of each of those networks. It's been our experience that as congestion occurs, latency starts to go up first linearly and then exponentially. So the first thing that we looked at, this is a graph showing over a 24-hour period the latency in milliseconds on at the 80th percentile on the consumer side, on the access side. And although there's a little bit of a difference between peak and off-peak, it isn't really all that different. There's about sort of 4 or 5 milliseconds difference between 4 a.m. and 4 p.m. Our conclusion there was that there was, again, no material systemic congestion in the access across the board on the top 100 web domains. But the answer was very different. Oh, that might have been a poor choice of color. The answer was very different when we looked at the internet side. And this is where our study group had a big dichotomy. Half of the players in our study group, this was completely flat on the internet transit and peering side over 24 hours, and the other half had this trend line. So this is an example where the trend line is shown, and what's happened is, as you go into the busy hour, the top 100 websites start to experience a material delay on the three-way handshake. And this, as we saw yesterday, that really affects the TCP load time quite a bit. And the conclusion we could draw from this is, although there's no material congestion in the access, we saw that from the video providers, there is material congestion in some of these providers at the peering and the interconnects and the CDN and so on to the web servers. And then the other thing that was a bit of a shocker for us is if you go back to the beginning of this talk, and I said, well, the way adaptive video works is it scales its bandwidth up and down. A lot of people didn't consider this. When TCP was sort of invented, it was a bulk transfer protocol. Nobody considered it having a rate. Nobody considered it having a positive feedback loop on how fast it could go. Nobody considered that I would have a TCP flow that if it didn't get enough bandwidth, it would actually switch to a different type of content that used less bandwidth. And if I gave it more bandwidth, it would switch to one that would use more. But of course, it's exactly what adaptive video's done. And what's happened is it doesn't play all that fairly with the short-lived web connections. So what happens is you get a TCP connection open to your 2-hour-long movie, and its window is wide open, and it's shoveling data down your throat, and it's never spending any time in TCP fast start. And then you open your little web connection, you go syn, synac, ACK, get, JPEG, fin. It spends half its time just getting up to speed. And that's what we're seeing on this chart, is a lot of people were thinking during times of congestion, adaptive video is getting out of the way. The conclusion we drew is exactly the opposite's happening. During times of congestion, your adaptive video stays wide open, delivers the same experience, but it pushes aside the short-lived flows because they are spending a lot more time in TCP handshaking. So the summary for this is, there's a paper that was linked on the beginning of this. You're welcome to read, or you can reach out to me afterwards. But we found there was a bunch of different independent decisions made by different players, and they were each affecting quality at different places. Some were done on purpose, some were done by accident, some were sort of in between. They knew about it, but it was complex to fix. And the second thing we found is the common quality benchmarks really weren't that good. They were a little bit flawed. They delivered pretty non-repeatable results, and a lot of people were making relatively broad business decisions based upon relatively noisy data. None were very accurate. And then the last thing we found is that the end user's quality of experience was actually a combination of those technical and commercial factors. So with that, I will take any questions.
Dave Temkin, Netflix. And I've got 4 questions, but as the person who helped author these rules, I will cede the mic to anyone else who'd like to interrupt me. So you point out that each ISP experienced a peak in Open Connect bandwidth every day in the early morning. You also point out that the timing is in peak per day in UTC, which I don't really understand the correlation there. But for a service that's only used basically in prime time, right? It's peak to trough. Doesn't that just make sense? I mean, it sounds you're trying to make sensational data out of how people use the service when it's not functionally equivalent to YouTube. Well, YouTube is something people use from their desk at work to waste 5 minutes. No one sits down and watches a 30-minute episode of whatever unless they want to get fired.
So I'll take your questions one by one. So on this one here, this is the per flow bandwidth, so it's normalized. So you're right, there's way less people watching at 5 a.m. And again, there may have been just something going on during the few-week study period we had here. But what you see on this chart is across a fairly large number of consumers and a fairly large amount of time. What it's just saying is that there is a greater per stream bandwidth delivered at 5 a.m. Than the average over the course of the day. So it has nothing to do with whether there's one person using it or a million people up early watching something. It's not trying to be sensational. It's just it was an observation on this data The other CDNs don't seem to show that.
Right, but you also you point out that the speed index is flawed because there's a peak at peak. Well, the speed index is specifically called out as what the average is at peak during the day. So you left that out in your description of what the speed index is.
Yeah, so I'm not trying to show this. So this correlates relatively closely to what you show on the speed index. When you run Hulu at the same time, Hulu's number on a per flow basis is higher than this.
Sure.
So the speed index is showing sort of the worst point over the course of the day, which is here we're seeing about 5 p.m. You see one of the CDNs has a drop, the level 3 one. And that's where the speed index is sort of latching onto as far as I could tell. The main conclusion we were trying to draw here is it did not seem to be an access bandwidth issue. That we were trying to take one independent variable at a time out of the equation. And I wasn't able to do all of them. In the study, we weren't hooked up to BGP AS path. So I'm sort of blind to how the data went in and out of the network. I know where it started, I know where it got to me, but I don't know how it shuffled in between there. That's one of the future things we want to do. But our conclusion there was that as a consumer, you should not take the Netflix speed index as a indication of the speed of your access line. It didn't seem to be correlated because
right.
the speedtest.net was also not correlated.
Netflix has never called it a way to quantify the access speed of your line. We've said it is how we get data to that network. And by not measuring the middle mile, this data is useless. I'm sorry. You've called out all sorts of things that really aren't directly relevant. I don't really see a lot of value in any of this data. Thank you.
That may be so. Again, I was trying to compare, by comparing Hulu, ESPN, and there was a dozen video providers here. What we were trying to do was to take one independent variable at a time. I'm open for other suggestions of better ways to measurement. On the UTC one was just an observation. There's nothing really interesting here other than what it's showing is that the East Coast and West Coast servers at the same instant, you would think that they would be 3 hours offset, but they're not. They're actually behaving in concert, but it's such a large amount of latency that I don't think it's actually a network effect, and I don't think it's a congestion effect. And since the quality of the video is not correlated to the latency, it's not a downside. I think it's just a function of the underlying technology that's there. So it's just an observation. It was one of the things that we were asked to look at in the study was whether there was any path changes over the time of the day, and it did not appear there was based on our conclusion.
So, I mean, if any network engineer in the room isn't aware that latency goes up as congestion goes up, I think you should probably look for a new job. When you look at that, your data honestly doesn't match mine. I would gladly present some data. This is my data guy right in front of me. He'll gladly speak to that. But when you say the study that you were asked to do, who asked you to do the study?
So this was something that twice a year we do something we call our global internet phenomena, which is a sort of track of the trends of consumer data in the world. One of the things that had come up in the various journalists that interviewed us was questions about how can you go deeper than just sort of, how much volume there is in different things. So sure. Out of those, there was a set of questions that we sort of correlated and said, all right, we're going to try to do something that's a little bit deeper. We're going to address quality as an issue. This isn't actually congestion-related timing here. This is on the TCP handshake only. So this isn't for the entire flow. This is just the first 3 packets. So as a consequence, A, it's not congestion because you can see it on ping and so on, but B, it's not necessarily a proxy for the large packets that are coming later. It was meant to be a proxy for are the servers moving around, and the short answer we came to was we don't think so.
The absolute worst time, and I'll cede the microphone after this, the absolute worst time for congestion for any TCP session is when you're setting it up. Thank you.
I don't think it is, but.
This is Dan Ellis from Netflix also. Have you had a chance to take a look at the MLabs data that has been recently published?
Yeah, so there's certainly starting to be some really good quality data come on the market between the FCC SAMNOs and some of the other regulators around the world. Singapore and the UK, they've done a really good job of getting sort of academics involved to get really good quality data. MLabs is another excellent project there. So that's one of the things that I keep an eye on. And their data sources are somewhat different than ours. Ours is based on passive observations, and they have the ability to do active tests. So I think it's a really good complement. But I think the MLabs one is an excellent way. It's much better set up than the speed test, but it's just not as widely known.
I think the MLabs data would probably be very helpful in you trying to track down the point of congestion. They do a good job of hitting it from multiple places and showing the levels of congestion.
Yeah.
Regarding the startup and having the highest latency or worst performance during startup, it is definitely something we've seen, especially as the latency is higher, or in very lossy situations as the latency is higher, or the packets are smaller, which is what happens in your initial startup. That probability of having that data get to the end user is the lowest.
Yeah, well, the TCP will retransmit after 3 seconds at that very early stage. We specifically excluded packet loss in here. We only looked at the latency of, because there's an ambiguity. If I get a response 3 seconds later, it's answering the first or the second. So we exclude that. We only look at the variations in latency for the handshake there. I don't think there's any network effect that makes a SYN packet have a different latency than a packet later in the flow. There's certainly effects on the server and so on. I think I've gotten the hook here.
Thank you.